Thank you all for joining us. And in this presentation, I'll be discussing hyperscaler design and verification. We're looking at large, complex hyperscaler designs that you would typically find in a data center environment with cloud-based computing platforms and artificial intelligence applications. So hyperscaler, these designs push our computing requirements to the extreme with our component and routing density, signal speed, power utilization, thermal dissipation, as well as high reliability requirements. For systems designers, these designs operate with extremely small voltage and timing margins, which means that we must accurately model critical structures with full wave electromagnetic solvers. And it's equally important that these simulations that we're running and these structures we're creating represent the board as it will be actually manufactured rather than just as we intend it and just as we thought we were designing it. So these high signal speeds and tight margins, they often require specialized stack-up materials and carefully optimized layouts. And these situations create a huge range of design possibilities that must be explored in order to find the best solution to meet our performance goals. So if we combine these challenges with tough competition and tight project deadlines, this design and verification process becomes a tough challenge. So the origin of this as designed versus as manufactured problem lies in the fact that our CAD databases model geometries with absolute precision, whereas in the physical world, we can't always manufacture those structures that way. So in practice, we're modeling and simulating structures like vias and traces with much more precision than we can actually manufacture physically. So this is often referred to as analytical overkill. Another significant problem is that the behavior of an electrical signal varies significantly based on how the board is manufactured. So if we take, for example, a strip line signal, the core, the side of that signal trace facing the core layer will be much smoother and therefore exhibit less loss, whereas the opposite side facing the prepreg layer of the stack-up will be much rougher and exhibit more loss. So it's critical that we model these rather subtle effects in order to build an accurate interconnect model for the nets that we're simulating. We can use tools like Z0 Z-Planar as an enterprise level stack-up design tool, as well as hyperlinks that I'm discussing today, to create better models of our as manufactured board right from the beginning, so leading to more accurate results later on. If you want to get any more information on both hyperlinks as well as Z0 Z-Planar stack-up design, you can talk to any of us Siemens staff and we can show you some more on the demo stations over there. So optimizing layout structures for these hyperscaler designs is extremely difficult due to the sheer number of design parameters that we're dealing with, as well as complex physical and electrical constraints. So specifically, BGA and connector breakout regions are tricky due to the limited space that we have to route signals and place vias down as we want. It's not always possible to manufacture them that way, so we need to find a blend between the design that we want to build versus what's actually possible to manufacture. The goal here is that we want to create a design that performs well under all of our possible manufacturing conditions. And we do that by choosing the correct set of parameters like drill size, antipad size, trace width, trace spacing, and so on. The problem is that this number of design parameters creates a massive design space with millions of possible combinations of design parameters. So traditional methods that we have like swept parameter analysis or Monte Carlo analysis aren't very practical in a case where we have millions of combinations of design parameters because it would take way too long to simulate all those possible cases. So the solution we have with hyperlinks is called design space exploration, or sometimes referred to as HLDSE. This uses AI-driven investigation algorithms to effectively explore our design space and find the best set of design parameters to meet our performance goals and targets. And the best part is that this solution can find a workable result of the desired design parameters in usually less than 100 simulations. So I want to take a quick look at this reference eval board that I'll be referencing later in the presentation. We ran some simulations on. This is the SDK 180 design. It's based on an AMD Versal Premium Series evaluation board called the VPK 180. This design is used to evaluate their Versal Premium Series adaptive SoC devices. It has support for multiple different optical transceivers operating at both 56 and 112 gigabits per second. It's got some onboard LPDDR4 memory, as well as some additional peripherals like USB and Ethernet networking. So we modified this board a bit and called it the Siemens STK 180 board. We designed the StackUp with Z0Z Planner, StackUp planning tool. We introduced some of our own manufacturing data, like back drilling for the via structures. And then we put the board in a mid-layout state. And what we see here in this image on the left is where only the most critical high-speed nets are routed so far on the board. And then finally, we introduced a few artificial errors into the layout so we could have our software hyperlinks find some issues in the design during analysis. So with our initial simulations, we analyzed 72 of these optical links operating at 56 gigabits per second with the CEI 56G VSR PAM4 protocol. So even when designers follow their PCB layout guidelines to a T and they're perfect, unfortunately mistakes still happen. And the problem is that these mistakes are random, so we can't necessarily catch all the mistakes just by picking out the shortest and the longest trace to simulate, or maybe just a small subset of signals. We really need to simulate everything to be able to find these errors. So the question then becomes, when we find an error, will we be able to catch these errors before it's too late? So traditional methods that we have, like manual inspection or building a detailed channel model for every single net on the board, can be very tedious, error-prone, time-consuming. There's a lot of human error introduced. So we really, in order to catch all of these issues and verify all of our signals, we really need to automate this process. So that being said, full automation of a system-level post layout board is a tall order. We have a lot of steps that need to take place here and all need to be automated. So if we look at what needs to take place, we need to identify the signals to be analyzed. We need of those signals, we need to find if there's any critical areas that need to be modeled in 3D. We then need to create and solve those 3D areas in our electromagnetic field solvers. We then stitch them back together with the rest of the channel to create an end-to-end topology model of our nets. We then identify the protocol and metrics associated with it for simulation. We then simulate those signals based on the protocol, and then finally move on to post-processing our results based on those metrics and creating any relevant simulation reports. So that's a lot of steps and a lot of work, and it's usually impossible to complete this manually with any sort of volume. So with hyperlinks, we're actually able to automate this process from front to back, and we're able to simulate and verify hundreds of channels, including 3D areas, with a single button push. So speaking of verifying those hundreds of channels and 3D areas, we need a way to solve those 3D EM projects. With traditional solving methods, that could take weeks of computational time. So, and the whole point of running this full layout, this post layout verification, is that we want to find issues early in the design cycle and be able to do something about them, be able to drive them back to layout and make sure our designs are set up correctly. So with hyperlinks, we're actually able to accelerate our solver jobs through job distribution. So in the first case, we can accelerate an individual job. If we're maybe just solving a few 3D areas, we could throw more cores at the problem to increase the solve time and solve them sequentially on a single machine. Their second use case is we could offload the job from a local machine, maybe to a more powerful server machine, and we could run multiple jobs, say 2 to 4 jobs in parallel, and accelerate our solve time that way. And then finally, the last case is if we're looking at the larger scale, trying to solve hundreds of areas at a time that could take weeks of solve time, is we could offload this onto multiple server machines, solve multiple jobs in parallel, or we could interface with a load management software to solve in a compute farm. So if we remember that STK 180 reference design that I mentioned, we were simulating initially 72 of those optical links. In those channels, we found and identified 93 3D areas that needed to be modeled in our full wave solver. So that would have taken 57.5 total computational hours if we were to solve those sequentially, but we were able to accelerate the solve more than 10x with a solve time of just under 5 hours, 4.79 hours there, by solving 12 of these areas in parallel on a Linux compute farm. So as we've discussed, the full system post-layout verification is a complicated process with a lot of steps going on. And so in order for the full system level analysis to have any sort of reliability, we need each individual step in that process to be incredibly reliable. If we consider an example here, we've got a system with 128 channels, 256 critical areas that have been identified that need to be modeled in 3D. Hyperlinks uses automatic pattern recognition of the areas so that we don't solve any duplicate areas more than once. So we were able to reduce that 256 critical areas down to 200 unique, distinct solves. So if we say, for sake of example, that we want the full system level process reliability to be 95% reliable, that means we want our system to run to completion with no errors 19 out of 20 times. The question is how reliable do we need the EM modeling step of this process to be? So that's just the EM modeling portion is one single step in this overall process. And the answer is we need it to be incredibly reliable. So that the area detection, the area modeling, the solving itself, and the post-processing of the results and creation of S parameter data for each of the areas, we need that to be 99.97% reliable in order to achieve this top level reliability of 95%. So if we step back and think about this for a minute, how many people have a 3D EM modeling solution that produces successful results 99.97% of the time? And the answer is most people don't, but Hyperlinks users do. So there's two major benefits to running these full system simulations that I've been talking about. The first is that we can perform the post-layout analysis to verify all of our signals on the board rather than just a select few of them, and we're able to find some of these random implementation errors in the system. And the second benefit is that we can show the impact of design trade-offs at the system level and how they affect all of the signals on the board. So in this plot we see on the right here, we're looking at the effect of drill performance on those 56G VSR channels. The blue dots show the set of signals simulated with a 12.3 mil via drill diameter. And then the set of green dots show those same signals simulated with a smaller 9.8 mil drill diameter. So at a quick glance, we're able to see the effect of the drill diameter change on the system level performance of all of these nets. And that plot is showing eye height versus eye width on the X and Y axis for those channels compared with the protocol requirement. So why do we think you should be using hyperlinks to design and verify your hyperscaler designs? First is design space exploration that we talked about. Hyperlinks allows you to explore these massive design spaces with millions of combinations of design parameters quickly and effectively. And we're able to create routing guidelines that help maximize our system level performance for all nets on the board. And if you're using Siemens Expedition for your layout tool, we're able to seamlessly drive these routing rules into layout. And then secondly is the post-layout verification capability. So with hyperlinks, we're able to verify all of the signals in the design, not just a select few. We have an automated process from front to back for the solution, and we have scalable, accelerated job distribution capability to be able to accelerate our solve time of our 3D EM projects. And then finally, we have a unique progressive verification methodology, which we'll actually discuss in a separate presentation. So with that, my name is Zach, and I want to thank you all for your time and attention and joining us today. And remember that it's easier with hyperlinks.